According to the 2020 National Electrical Code, a single large circuit breaker is required between the transformer secondary and the 620 amp circuit breakers. Article 450.3 states a transformer secondary overcurrent protection must be provided to protect the transformer from overloads and short circuits. Article 450.3b2 specifies that overcurrent protection for transformer secondary circuits must be sized based on the transformer capacity per Table 450.3b2. For a 45 kVA transformer with a secondary voltage of 208V/120 volts, the overcurrent protection must be rated at not less than 225 amps, according to the table. Here's the reasoning. The maximum load current for the 620 amp circuits is calculated as 6 circuits multiplied by 20 amps per circuit, equaling 120 amps. The required secondary transformer overcurrent protection is determined by the transformer capacity. According to Table 450.3b2, this is 225 amps. Since the required secondary transformer overcurrent protection, which is 225 amps, is greater than the maximum load current, which is 120 amps, a single large circuit breaker is required between the transformer secondary and the 620 amp circuit breakers. This circuit breaker should be rated at 225 amps as per the National Electrical Code. To elaborate further on transformer protection based on the National Electrical Code, it's crucial to understand the purpose and implementation of overcurrent protection devices, or OCPs. These devices, such as circuit breakers and fuses, are designed to protect electrical equipment from damage caused by excessive current flow, which can result from overloads, short circuits, or ground faults. In the context of transformer secondary protection, the NEC provides specific guidelines in Article 450.3b to ensure that transformers are adequately protected. The primary goal of transformer secondary protection is twofold. Firstly, to protect the transformer itself from overheating and potential failure due to sustained overloads or fault currents, and secondly, to protect the downstream circuits and equipment connected to the transformer secondary from the effects of excessive current. Article 450.3 establishes the fundamental requirement for providing overcurrent protection on the secondary side of a transformer. This protection is essential because transformers are susceptible to damage from both overload conditions, where the current demand exceeds the transformer's rated capacity, and short-circuit conditions, where a low-impedance fault path causes a rapid and substantial increase in current. Without adequate overcurrent protection, these conditions can lead to insulation breakdown, winding damage, and even catastrophic failure of the transformer. Article 450.3b2 provides more specific guidance on how to size the overcurrent protection for transformer secondary circuits. It mandates that the overcurrent protection device must be sized based on the transformer's capacity as detailed in Table 450.3b2. This table correlates transformer kVA ratings and secondary voltages with the maximum allowable rating or setting of the overcurrent protection device. The table values are based on calculations that consider the transformer's full load current and a safety factor to account for transient conditions and variations in load. Using Table 450.3b2 to determine the appropriate overcurrent protection for a 45 kVA transformer with a 208V/120 volt secondary involves finding the corresponding value in the table. In this case, the table specifies that the overcurrent protection device must be rated at not less than 225 amps. This means that the circuit breaker or fuse protecting the transformer secondary must have a rating of 225 amps or higher. The calculation provided, 6 circuits multiplied by 20 amps per circuit equals 120 amps, represents the total connected load in the transformer secondary. However, this value is not the sole determinant of the required overcurrent protection. The NEC mandates that the overcurrent protection be sized based on the transformer's capacity, not just the connected load. This is because the transformer must be protected from overloads that may occur even if the connected load is less than the transformer's rated capacity. The conclusion that a single large circuit breaker rated at 225 amps is required between the transformer secondary and the 620 amp circuit breakers is based on the comparison between the required overcurrent protection, 225 amps, and the maximum connected load, 120 amps. Since the required overcurrent protection is greater than the maximum connected load, the 225 amp circuit breaker is necessary to provide adequate protection for the transformer. In addition to the specific requirements outlined in Article 450.3b, there are other considerations that may influence the selection and installation of transformer secondary overcurrent protection. These include the interrupting rating of the circuit breaker or fuse, the coordination of overcurrent protection devices, and the specific application of the transformer. The interrupting rating of the overcurrent protection device must be sufficient to safely interrupt the maximum fault current that could occur at the transformer secondary. This rating is typically expressed in amps and represents the device's ability to clear a fault without failing or causing damage to other equipment. Coordinating overcurrent protection devices involves selecting and setting the devices so that they operate in a coordinated manner to minimize the extent of an outage. This means that the overcurrent protection device closest to the fault should operate first, isolating the fault and allowing the rest of the system to continue operating. The specific application of the transformer may also influence the selection of overcurrent protection. For example, transformers used in critical applications such as hospitals or data centers may require redundant overcurrent protection or more stringent protection settings to ensure a high level of reliability. Furthermore, it is important to note that the NEC is a minimum standard, and local codes or regulations may impose additional requirements for transformer protection. Therefore, it is essential to consult with local authorities and qualified electrical professionals to ensure compliance with all applicable codes and regulations. Let's delve deeper into the practical implications of these NEC requirements. Imagine a scenario where the 45 kVA transformer is supplying power to a panel board that feeds several branch circuits. These branch circuits could be powering lighting, receptacles, and small appliances in a commercial building. Each of the 620 amp circuit breakers in the panel board is protecting a branch circuit from overloads and short circuits. However, these branch circuit breakers do not provide adequate protection for the transformer itself. If a fault occurs on one of the branch circuits, the corresponding 20 amp circuit breaker will trip, isolating the fault. However, if a more severe fault occurs, such as a short circuit within the panel board or a ground fault on the transformer secondary, the current could quickly exceed the transformer's capacity and cause damage. This is where the 225 amp circuit breaker comes into play. It acts as a backup protection device, safeguarding the transformer from excessive current that could result from a major fault. The 225 amp circuit breaker is sized to allow the transformer to operate at its full rated capacity without tripping unnecessarily. However, if the current exceeds 225 amps, the circuit breaker will trip, protecting the transformer from damage. In addition to protecting the transformer from overloads and short circuits, the 225 amp circuit breaker also provides a degree of protection against ground faults. A ground fault occurs when an unintentional connection is made between a live conductor and ground. This can result in a dangerous flow of current that can pose a shock hazard to personnel and damage equipment. The 225 amp circuit breaker is typically equipped with ground fault protection, which senses the imbalance in current between the phase conductors and the neutral conductor. If a ground fault is detected, the circuit breaker will trip, interrupting the flow of current and reducing the risk of electrical shock and fire. It is important to note that the 225 amp circuit breaker must be properly installed and maintained to ensure its effectiveness. This includes verifying that the circuit breaker is correctly sized for the transformer, that the connections are tight and secure, and that the circuit breaker is tested periodically to ensure that it is functioning properly. In summary, the NEC requirements for transformer secondary protection are designed to protect transformers from overloads, short circuits, and ground faults. These requirements are based on the transformer's capacity and the need to provide a coordinated protection scheme that minimizes the extent of an outage. By understanding and implementing these requirements, electrical professionals can ensure the safe and reliable operation of electrical systems. To further clarify the concepts, let's consider some additional examples and scenarios. Suppose the 45 kVA transformer is supplying power to a motor control center that controls several motors in an industrial facility. The motors are used to drive pumps, fans, and other equipment. Each motor is protected by its own overcurrent protection device, such as a motor starter with overload relays. However, the motor starters do not provide adequate protection for the transformer itself. If a fault occurs in one of the motors, the corresponding motor starter will trip, isolating the fault. However, if a more severe fault occurs, such as a short circuit within the motor control center or a ground fault in the transformer secondary, the current could quickly exceed the transformer's capacity and cause damage. Again, the 225 amp circuit breaker acts as a backup protection device, safeguarding the transformer from excessive current that could result from a major fault. A 225 amp circuit breaker is sized to allow the transformer to operate at its full rated capacity without tripping unnecessarily. However, if the current exceeds 225 amps, the circuit breaker will trip, protecting the transformer from damage. In this scenario, it is particularly important to coordinate the overcurrent protection devices to minimize the extent of an outage. The motor starter should be set to trip before the 225 amp circuit breaker trips, so that a fault in a motor will only interrupt the power to that motor rather than shutting down the entire motor control center. This can be achieved by carefully selecting the settings of the overload relays in the motor starters and the time current characteristics of the 225 amp circuit breaker. Another scenario involves a 45 kVA transformer supplying power to a data center. Data centers are critical facilities that require a high level of reliability and uptime. In this case, it may be necessary to provide redundant overcurrent protection for the transformer to ensure that a single fault does not cause a complete outage. Redundant overcurrent protection can be achieved by installing two 225 amp circuit breakers in parallel, each with its own set of current transformers and protective relays. If one circuit breaker fails, the other circuit breaker will continue to provide protection for the transformer. In addition to redundant overcurrent protection, data centers may also require more stringent protection settings to minimize the risk of nuisance tripping. Nuisance tripping occurs when a circuit breaker trips unnecessarily due to transient conditions or minor disturbances in the electrical system. To minimize nuisance tripping, the 225 amp circuit breaker can be equipped with advanced protective relays that are less sensitive to transient conditions. These relays can distinguish between actual faults and harmless disturbances, preventing the circuit breaker from tripping unnecessarily. Furthermore, it is essential to perform regular maintenance and testing on the transformer and the overcurrent protection devices to ensure that they are functioning properly. This includes inspecting the transformer for signs of damage, testing the insulation resistance of the windings, and verifying the calibration of the protective relays. By implementing these measures, data centers can ensure the highest level of reliability and uptime. In conclusion, the NEC requirements for transformer secondary protection are essential for ensuring the safe and reliable operation of electrical systems. These requirements are based on the transformer's capacity, the need to provide a coordinated protection scheme, and the specific application of the transformer. By understanding and implementing these requirements, electrical professionals can protect transformers from overloads, short circuits, and ground faults, and minimize the risk of electrical hazards. It is also crucial to stay up to date on the latest revisions to the NEC and to consult with qualified electrical professionals to ensure compliance with all applicable codes and regulations. The National Electrical Code is updated every 3 years, and it is important to be aware of any changes that may affect transformer protection requirements. Additionally, local codes and regulations may impose additional requirements that are not covered in the NEC. Therefore, it is always best to consult with local authorities and qualified electrical professionals to ensure that all applicable codes and regulations are followed. Understanding the application of overcurrent protection for transformers involves several key aspects, including the transformer's kVA rating, primary and secondary voltages, and the specific load characteristics it serves. Let's delve deeper into each of these aspects to provide a comprehensive understanding. The kVA rating of a transformer, in this case 45 kVA, represents its apparent power capacity. This value is crucial for determining the transformer's full load current, which is the basis for sizing the overcurrent protection devices. The full load current can be calculated using the following formula for single-phase transformers: amps equals kVA times 1000 divided by volts. For three-phase transformers, amps equals kVA times 1000 divided by volts times the square root of 3. In this example, the transformer has a primary voltage of 480 volts and a secondary voltage of 208Y/120 volts. The primary voltage is the voltage supplied to the transformer's input winding, while the secondary voltage is the voltage available at the transformer's output winding. The 208Y/120 volt designation indicates that the secondary winding is a three-phase 4-wire system with a line-to-line voltage of 208 volts and a line-to-neutral voltage of 120 volts. Knowing both the primary and secondary voltages is essential for selecting the appropriate overcurrent protection devices for both sides of the transformer. The load characteristics that the transformer serves also play a significant role in determining the overcurrent protection requirements. The load can be either linear or nonlinear, and it can consist of various types of equipment, such as lighting, motors, and electronic devices. Linear loads draw current in a sinusoidal waveform, while nonlinear loads draw current in the non-sinusoidal waveform. Nonlinear loads, such as electronic devices with switching power supplies, can generate harmonic currents that can overload the transformer and cause it to overheat. In such cases, it may be necessary to direct the transformer or to install harmonic filters to mitigate the effects of the harmonic current. In addition to the load characteristics, the ambient temperature and the transformer's cooling method must also be considered when selecting the overcurrent protection devices. Transformers are typically designed to operate at a specific ambient temperature, and if the ambient temperature exceeds this value, the transformer's capacity must be derated. Similarly, the transformer's cooling method, whether it is air-cooled or liquid-cooled, affects its ability to dissipate heat and its overall capacity. Once all of these factors have been considered, the appropriate overcurrent protection devices can be selected for both the primary and secondary sides of the transformer. The primary side overcurrent protection is typically provided by a fuse or a circuit breaker that is sized to protect the transformer from overloads and short circuits on the primary side. The secondary side overcurrent protection is typically provided by a circuit breaker or a set of fuses that are sized to protect the transformer from overloads and short circuits on the secondary side. The secondary side overcurrent protection must also be coordinated with the branch circuit overcurrent protection devices to ensure that a fault on a branch circuit will trip the branch circuit overcurrent protection device before it trips the secondary side overcurrent protection device. This coordination helps to minimize the extent of an outage and to prevent unnecessary tripping of the secondary side overcurrent protection device. In addition to the overcurrent protection devices, transformers may also be equipped with other protection devices, such as thermal overload relays and sudden pressure relays. Thermal overload relays protect the transformer from overheating due to prolonged overloads. Sudden pressure relays protect the transformer from internal faults that can cause a rapid increase in pressure inside the transformer tank. These additional protection devices can help to extend the life of the transformer and to prevent catastrophic failures. Finally, it is important to perform regular maintenance and testing on the transformer and its protection devices to ensure that they are functioning properly. This includes inspecting the transformer for signs of damage, testing the insulation resistance of the windings, and verifying the calibration of the overcurrent protection devices. By performing regular maintenance and testing, it is possible to identify and correct potential problems before they can lead to a failure. To further emphasize the practical aspects of transformer protection, consider the following real-world scenarios. Firstly, a transformer supplying power to a hospital. Hospitals are critical facilities that require a high level of reliability and uptime. In this case, the transformer must be protected from overloads, short circuits, and ground faults. The overcurrent protection devices must be carefully selected and coordinated to ensure that a fault on one branch circuit will not interrupt the power to the entire hospital. Secondly, a transformer supplying power to a data center. Data centers are also critical facilities that require a high level of reliability and uptime. In this case, the transformer must be protected from overloads, short circuits, ground faults, and harmonic currents. The overcurrent protection devices must be carefully selected and coordinated to ensure that a fault on one branch circuit will not interrupt the power to the entire data center. Harmonic filters may also be required to mitigate the effects of harmonic currents generated by the electronic equipment in the data center. Thirdly, a transformer supplying power to an industrial plant. Industrial plants often have large motor loads that can cause voltage sags and harmonic currents. In this case, the transformer must be protected from overloads, short circuits, ground faults, voltage sags, and harmonic currents. The overcurrent protection devices must be carefully selected and coordinated to ensure that a fault on one motor will not interrupt the power to the entire plant. Voltage sag correction equipment and harmonic filters may also be required to mitigate the effects of voltage sags and harmonic currents. In each of these scenarios, the specific protection requirements will depend on the characteristics of the load and the criticality of the application. It is essential to consult with qualified electrical engineers and to follow all applicable codes and standards to ensure that the transformer is adequately protected. Let's explore the specific requirements of National Electrical Code Table 450.3b2 in more detail. This table provides guidance on the maximum rating or setting of overcurrent protection devices for transformers based on their kVA rating and secondary voltage. The table is divided into two sections, one for transformers with primary overcurrent protection only and one for transformers with both primary and secondary overcurrent protection. In the case of a 45 kVA transformer with a 208Y/120 volt secondary, the table specifies that the overcurrent protection device on the secondary side must be rated at not more than 125% of the transformer's rated secondary current. This means that the maximum allowable rating of the overcurrent protection device is calculated as follows. Firstly, calculate the transformer's rated secondary current using the formula amps equals kVA times 1000 divided by volts times the square root of 3. In this case, the rated secondary current is 45 kVA times 1000 divided by 208 volts times the square root of 3, which equals 125 amps. Secondly, multiply the rated secondary current by 1.25 to obtain the maximum allowable rating of the overcurrent protection device. In this case, 125 amps times 1.25 equals 156.25 amps. Therefore, the overcurrent protection device on the secondary side of the 45 kVA transformer must be rated at not more than 156.25 amps. However, the NEC allows the use of the next higher standard overcurrent protection device rating if the calculated rating does not correspond to a standard size. In this case, the next higher standard overcurrent protection device rating is 175 amps. Therefore, a 175 amp circuit breaker or set of fuses would be permitted on the secondary side of the 45 kVA transformer. It is important to note that this is the maximum allowable rating of the overcurrent protection device. The actual rating of the overcurrent protection device may be lower, depending on the characteristics of the load and the coordination requirements. The NEC also provides guidance on the location of the overcurrent protection devices. The overcurrent protection device on the secondary side of the transformer must be located as close as practicable to the transformer terminals. This helps to protect the transformer from faults that may occur in the conductors between the transformer and the overcurrent protection device. In addition to the overcurrent protection requirements, the NEC also provides requirements for grounding transformers. Transformers must be grounded in accordance with Article 250 of the NEC. Grounding helps to protect personnel from electrical shock and to prevent damage to equipment. The specific grounding requirements depend on the type of transformer and the wiring system. In the case of a 208Y/120 volt system, the neutral conductor must be grounded at the transformer and at the service entrance. This provides a low impedance path for ground fault currents to flow, which helps to trip the overcurrent protection devices quickly and to minimize the risk of electrical shock. The grounding conductor must be sized in accordance with NEC Table 250.122. The size of the grounding conductor depends on the size of the ungrounded conductors. It is essential to follow all applicable NEC requirements for grounding transformers to ensure the safety and reliability of the electrical system. Let's consider the practical implications of these grounding requirements in the context of a 45 kVA transformer with a 208Y/120 volt secondary. The neutral conductor from the transformer secondary must be connected to a grounding electrode system. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode system must be bonded to the building's metal frame and to any other metallic objects that are likely to become energized. This bonding helps to create a common ground potential throughout the building, which reduces the risk of electrical shock. The size of the grounding electrode conductor must be determined in accordance with NEC Table 250.66. The size of the grounding electrode conductor depends on the size of the service entrance conductors. In addition to the grounding electrode conductor, a bonding jumper must be installed between the transformer neutral and the equipment grounding conductor. The equipment grounding conductor is used to ground the metal enclosures of electrical equipment, such as panel boards, motors, and lighting fixtures. The bonding jumper ensures that the equipment grounding conductor is at the same potential as the transformer neutral. The size of the bonding jumper must be determined in accordance with NEC Table 250.102. The size of the bonding jumper depends on the size of the largest ungrounded conductor. By following these grounding requirements, it is possible to create a safe and reliable electrical system that protects personnel from electrical shock and prevents damage to equipment. It is also important to perform regular inspections and testing of the grounding system to ensure that it is functioning properly. This includes visually inspecting the grounding connections for signs of corrosion or damage and testing the impedance of the grounding system to ensure that it is within acceptable limits. Regular maintenance and testing of the grounding system can help to identify and correct potential problems before they can lead to a failure.